My name is Daniel Hashmi, candidate number 8244. This is my submission for the A-level AQA Computer Science NEA project, which is a macroeconomic simulation system. This is the testing video and getting into the first test. I'll be conducting the first three tests simultaneously, the first test being a defensive input validation. So when the user enters an input which the system doesn't allow, an error message should be shown and the simulation should be prevented. The second test being a boundary testing on policy inputs. So for certain minimum bounds, for example, for a negative interest rate, a message box should be shown and the simulation is prevented. For unrealistic bounds, for example, if the user tries to insert a tax rate of 2,000, which is highly unrealistic, a message box will be shown, but the simulation is still accepted, and the user has option to either decline or accept their chosen input. And the third and final test we'll be doing is toggle and expander functionality. So in the control panel, which you'll see in a second, the user should be able to untoggle and toggle the control panel to access more inputs, and as it says here, additional fields should become enabled. So moving on to the program, this is the menu screen with 5 different tab options: start simulation, history and analysis, load scenario, help and instructions, and settings. To access the graphs, and for this simulation we'll be using the first tab, start simulation. So getting into it, you are defaulted to GDP over time graph. Users have an option of 4 additional graphs: Okun's graph, output gap versus inflation, debt to GDP, and current account balance. And this is the control policy panel we talked about earlier. So for example, here we have an interest rate of 3%. How about if we were to enter 3 as a number, as a word? An invalid input, please enter a real number. So message box is displayed to the user. How about if we were to enter an input of -3, which is impossible because interest rates cannot be set negative. Interest rate cannot be less than 0, and as you can see, the message box is tailored to whatever input you are trying to insert. How about if we had an interest rate of 3,000? Once again, something that would never happen in the real world. Interest rate is outside a realistic range, 0 to 17. Do you want to proceed? So the user has the option to continue to proceed or decline. For the sake of this, we won't be accepting that. There are also 2 policies which the user can enable advanced options, which will enable the toggle functionality. So we have monetary policy, which has an advanced mode, and fiscal policy, which has an advanced mode. So if we enable both of these, we should be able to toggle and untoggle each one. And same with interest rate, all these text boxes are wired up with the same approach. So if we were to set an inflation target of 2 as a string, invalid input, please enter a real number. An input of -2, once again, inflation target cannot be negative integer, inflation target cannot be less than 0. Once again, tailored to whatever text box you're trying to enter. And then if we were to choose 2000, inflation target is outside a realistic range of 1 to 41 to proceed. And we can test this out for every single one of these inputs, core parameters as well. 0.6. As you can see, a message box is displayed, but we'll keep that. And then same with the simulate many, there is a cap of 50 years that can be simulated at any one time. So if the user was to enter 51, for example, try to simulate, succeeds a one-time simulation max, try 50 or less. So we can see that if we enter 50, I won't show the simulation simulate many functionality yet, but that will come later in the video. So on that basis, we can mark the first 3 tests as a pass. Moving on to the 4th test, which is testing the simulation of each graph. So all graphs should be able to render upon simulation, button press, and importantly show the same simulation state. So if I was to simulate 10 years on this graph GDP over time, I should be able to switch to any of these 4 graphs and it should show 10 data points on the graphs. So we'll start off with a smaller number. So if I simulate 5 times, see 5 points, Oken's graph, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, and 5. And if we return back to GDP over time, you can still see that the graph has persisted and remained the same with 5 points in the exact same locations. So on that basis, we can also mark this test as a pass. Now for the 5th test, is that to confirm that the plotted graph values match the values which are in the text file. So graph points should be placed in an appropriate place which aligns with the values in the text file. So we'll use GDP over time because this is the easiest graph to kind of display and match up with the text file. So once again, I can simulate 2025. So you can see the first point is a little bit over 2000, so around between 2000 and 2100. That's what appears on the axis. And if we check the real value in the text file, you can see between 2000 and 2100 as displayed on the graph, so 2052.9. And then to continue, if we were to keep going 4 places, okay, let's get to the end of the graph. So at 2033, we have a GDP of around 2,200 as displayed on the axis approximately. And then if we head back to the text file, yep, around 2,200 is the GDP value. So we can confirm that the graph points do match the values of the text file. And we can just do for one more test, we can look at current account balance. So you can see the first year is just above 0.4, so maybe around 0.5, minus 5, minus 6% of GDP at 2025. So if you match that with the values of the text file, and you can see current account, yep, minus 5.43 and minus 4.78, which matches up with the values that we see on the axis. So on that basis, we can reset the simulation and then declare this test as a pass, which we already have. The next test being the simulate many button. So the user should be able to enter n number of years, where n is an integer, and the simulation system should be able to plot that many years on the graphs. So if the user was to enter, let's say, 10 years of simulation, as you can see, it simulates 10 times, carry across all graphs. We have 10 points for each graph. So on that basis, we can mark this one as a pass as well. The next test is the rolling window mechanism. So the window should be able to move vertically and horizontally when the graph reaches its borders. So what I mean by this is that you can see that the current max amount of points that can be displayed at any one time is 10. So if we simulate 10 years, we have 10 points. So now when I press the simulation button once more, 2025 should move to 2026 and 2034 should move to 2035. That way the graph continues to roll no matter how many years the user simulates, and it always shows the current 10 years. The number of points that can be displayed at any one time on the graph can be changed by settings, and we'll try that out later. But to test this functionality first, if I press simulate, you can see that 2025 has changed to 2026 and 2034 has changed to 2035. So we've tested the horizontal rolling window mechanism. And now we can test the vertical one. If we simulate 10 years, you can see once I simulate 10 years again, 4,000 should move up, and same with 0, 0 should move up. So the y-axis labels change in correspondence to how the trend line is moving. So as you can see, 4,000 changed to 4,554 as a max, and 0 is changed to 554. So we moved up in an increment of 554, and it'll keep going, and it'll keep going, and it'll keep going. So you can see that the graph is dynamic and changes in accordance to the trajectory of the trend line. So for that reason, we can mark test 7 as a pass. Getting into the policy tests, so we have increasing interest rates should decrease GDP, and we can see that by decreasing GDP in the text file or the trend line dropping. So for this test, we will remain GDP, we will remain interest rate at 3% for the first test, and we will simulate 10 years. So if we simulate 10 years with a 3% interest rate, this is the kind of trajectory that we have of the GDP over time trend line. To save us going to text file, we can look at the analysis, and we can see it starts on around about 2000 from 2025 and ends at around 2300. Now if we reset the GDP over time and we change interest rates to 12%, significantly higher than 3%, we should see a decrease in the trajectory of the trend line and a decrease in GDP overall. So as you can see, GDP has spiked down, smoother trend line, but once again reaches just about over 2000 within 10 years, which is a lot lower than before, and we can check this. So it starts around 1900 for GDP starting simulation value after 2024, and we finish around 2.1, which is a lot lower than the previous 2300 value that we had. So as you can see, when we increase interest rates, GDP does decrease, so we can mark this as pass. The second test, test 9, is that increasing interest rates should increase unemployment by at least 1%. So once again, if we reset the simulation back to a 3% interest rate, we can simulate 20 years, and we can view the average unemployment over those 20 years and compare it to a high interest rate, and there should be increase in the average unemployment rate over 20 years between the two different types of interest rates. So with a low interest rate of 3%, if we simulate 20 years, go to analysis, we can see that the average unemployment was 4.2 for those 20 years with a 3% interest rate. Going back and resetting the simulation, we can set a 12% interest rate, 20 years simulation period. Head over to analysis, and we can see that unemployment has skyrocketed to 19.88 over the 20 years. So for that reason, we can mark this one as a pass as well. The next test, test number 10, increasing tax rate should decrease GDP and decrease the trend line. So the same outcome as test 8, but with increase in tax rate instead. So you can see with a starting initial tax rate value of 20%, if we simulate 20 years within the simulation period, we can mark down the trend line of a 20% tax rate starting at 2,400 within the first 10 years, and then by 20 years we are nearing 2,800. Looking at the figures, we can see that after the first initial value of 2,000, we start the simulation period on nearing 2,000 GDP, and then ending near 3,000. Resetting the simulation and setting a tax rate of 40%. We should see a decrease in GDP and a decrease in the trend line over time compared to that of the 20% tax rate. So simulating 20 years of the period, we can see that GDP has decreased in terms of the trend line. The trend line is lower than it was before with the 20% tax rate. When we analyze, we can see that it starts off at around 1.9, which is lower than the 2,000 it was on previously, and it ends at 2,950, which was lower than I think it was 2,980, which was before. We can view the effects of this even more if we increase to a unrealistic tax rate like maybe 60%. If we simulate 20 years again, once again a decrease in GDP trajectory. Look at the analysis, 1.8, so we can see GDP has gone down a side value, and 2.9 for yeah. So a decrease in GDP over time as we increase tax rate, so we can mark this test as a pass. Test number 11 is increasing spending. So when you increase spending, GDP and debt should increase simultaneously. So we can test this out. We can start off with the initial spending of 22%, which the simulation has pre-prepared, and we can simulate 10 years of the simulation and see what happens. So we can see steady growth in GDP, and moving debt GDP. We can see a positive, steeper gradient in debt growth over time. Looking at the actual figures, we move from 2052 to 2,327 for GDP, and debt increases from 90.75 to 154.71. Now resetting and setting spending to 40%. You should see higher values in GDP and higher values in debt. So simulating 10 years. So we can see that debt has already reached its upper bound, but we will continue anyway. So we can look at the trajectory of debt. It's a lot higher than it was before, especially with a much steeper gradient and higher values overall. Looking at the GDP over time trajectory, you can still see a steady growth in GDP, although it is shallower, it's still a steady growth, which is what we mark down to observe. Looking at the analysis tab, we can see a growth in GDP from 2.1 to 2.3, which is steady growth rates, and from debt, we've gone from 102 to 276, so more than doubled over the 10-year period, which indicates a strong growth in debt, which is what we expected to see. Hence, we can mark test 11 as a pass. Test 12 is balanced budget stability. So setting the spending equal to taxation should mean that the government balance is in equilibrium and debt decreases whilst GDP grows steadily. So we can observe this. So resetting the simulation to 20 and 22%. We can set tax rate to 22%. So now it matches that of the spending proportion of GDP. And simulating 30 years of the simulation. We can observe what happens on GDP over time graph over those 30 years. So as you can see, GDP is growing steadily at positive growth rates. And if we switch over to debt to GDP, we can see a decline in debt over time due to the government balance being in equilibrium, 22 and 22%. And now we can view the results if the balance was in equilibrium. When we revert back to a 20% tax rate and a 22% spending of GDP, this line should be higher up, and GDP over time should be a bit lower down. So resetting the simulation, going back to GDP over time and simulating 30 years. As you can see, GDP is higher over time, and the debt to GDP ratio over time is a higher trend line. Before, the trend line was around here, heading downwards, but now it's moved up one. So for that reason, we can mark this as a pass, because when we set the spending equal to taxation, debt decreased over time more faster than how it was when we were in a balanced deficit and GDP remained to grow steadily. The next test is increasing base growth, which is a core parameter in economic simulation, and this should lead to higher GDP growth. This is quite an important variable when it comes to testing growth over time. So we can start off with the base growth initialization of 2%. And if we simulate 15 years of the simulation, we can see the effects now. So once again, upward trajectory trend line. Viewing the analysis, we start at 2052 and end at 2,700. Now, if we reset the simulation and increase base growth to, let's say, 5%, you should see an increase in the trajectory with a steeper gradient for GDP over time, indicating stronger growth over time. And we can compare that in the analysis tab. So as you can see, we have a steeper gradient in GDP. GDP is growing faster exponentially over time. And then viewing down the analysis tab, we can see an increase in GDP growth from 2061 to 3.6 thousand over the 15-year period. So we can see that when we increase base growth, there is positive correlation between higher GDP growth. So we can mark test 13 as a pass. Now, test 14 is increasing MPC should lead to higher GDP volatility. And the way we can measure GDP volatility is that we should see a higher increase between the starting year of the simulation and the ending year of the simulation. And if we see a higher increase after increasing MPC, we can indicate that GDP has become more volatile over that period. So with the stochastic shocks enabled, we can test out with the 0.6 MPC first of all, and we can observe GDP. So simulating 30 years we will do. And viewing analysis, we can see an average GDP growth of 2.796 over that period. And we can see a starting value of 2052 and an ending value of near 4,000. Increasing MPC should increase these values and the overall average GDP growth. So we can choose an MPC of 0.9, still with the shocks enabled, and simulate 30 years. Here we have an average GDP growth higher of 2,815.66, and we can see a higher average GDP growth from 2059 to, once again, near 4K. So for that reason, we can mark increase in MPC as a pass, as it leads to higher GDP growth volatility over time. Test 15 is that increasing Oken's beta coefficient should lead to a shallower regression slope and a similar / higher R-squared coefficient value. So going back to the GDP over time trend graph, we can look and test the first Oken beta coefficient of 0.3. And simulating 40 years of this should, if we switch over to Oken's graph for a more appropriate representation. So simulating 40 years with an Oken coefficient of 0.3, simulate this 40 years and we run a regression. We can see an R-squared coefficient value of 0.3 and we can see a gradient of negative 1.54. So after increasing Oken's beta coefficient, we should see a similar R-squared value, 0.3, give or take 5%, and a gradient which is shallower than negative 5.4, i.e. it's larger than negative 1.54. So we can increase the Oken beta coefficient to 0.5, and now once again, simulating 40 years, running the regression, we can see a shallower gradient of 1.1, which is less than the 1.54, and then we can see a correlation R-squared strength of 0.35, which was within the 5% give or take boundary. So when we increased Oken's beta coefficient, we had a shallower regression gradient with a similar to higher R-squared value, so we can mark that as a pass. We want to test 16, and this is testing the effect of debt drift. So we'll be testing the simulation without any debt drift and seeing how that affects with some value of debt drift. And when we increase debt drift from 0 to whatever value will be increasing to, debt should rise when drift increases, showing a higher trend line. So if we reset the simulation and we navigate to debt to GDP and advanced fiscal. We can see, oh, it was in core parameters. You can see a debt drift coefficient 0.01. So if we change that to 0%, just so we can test debt drift of 0, we can simulate 30 as a simulation and observe what happens. So we have a near straight downward trajectory debt to GDP graph, and after increasing debt drift to a value higher than 0, we should see this trend line is higher up than it was currently, so it should be above this 125 marks around here. So setting the debt drift to 0.3, simulating 30 years, and we can see debt drift's a lot higher. To keep it within the balance, we will use a lower value for debt drift. So we can use starting value of 0.01, and we can still see a higher trend line. So once again, 156 was a lot higher than the initial starting value of 120 it was when we had 0 debt drift, and we can see that when we increase debt drift, cumulative total debt increases over time and is higher over time. Although debt is decreasing over time, it's decreasing at a slower rate than it was before. So we can mark this as a pass. Test 17, increasing the debt rule strength should lead to a lower debt trend line as policy is more responsive to an increase in debt. So if we enable fiscal advanced settings to access debt rule strength, so we currently have a value of 0.06, and we can move that down to 0.01 to start off with. And we can also set spending target 28% and debt target to 60% to make more desirable conditions to make this test stand out more. So simulating 30 years, we can note the average debt level and compare it to when we have a higher debt rule strength. Viewing analysis, we can see that debt has increased from 94 to 163, and when we increase debt rule strength, we should see a lower ending value of a lower than 160 as policy acts more responsibly to reduce debt. So resetting the simulation, enabling advanced fiscal policy, and once again setting the spending target to 28%, and setting the debt target to 60%. And now we have debt rule strength of 0.06, which we can increase to 0.15. And testing it out, we should have lower debt values all across the board. Once again, very, very low, sub 96. And looking at analysis, we can analyze the debt, see the debt ends off as 71. So debt has actually decreased over a 30-year period instead of increased from 90 to 71. So we can see that increase in debt rule strength over time will decrease total debt accumulated. So we can mark this test as a pass. Now moving on to test 18, increasing automatic stabilizers should lead to a smoother GDP trend line as policy acts automatically within recessions and within downturns to bring back up GDP. So we should see smoother GDP trend lines, less volatility, and less uncertainty. So resetting the simulation back and enabling advanced fiscal settings. So we have the stochastic shocks enabled so we can test out the automatic stabilizers, changing the advanced fiscal settings. So we currently have an automatic stabilizer strength of 0.25 and we can set this to 0.05 to mark the difference in automatic stabilizer strength. Now we can simulate 40 years and witness how GDP trend line changes over time. For this test, we will be changing the rolling graph display to 20 years. Allows us to kind of analyze the volatility over time better. So simulating 40 years with an automatic stabilized strength of 0.05. So we can see it starts to plateau here and become more straight. There is some volatility at the start. If we decrease this, we can go back and test it with less years. So 0.05. And we can simulate 20 years this time around, and we can see still upwards trajectory overall, but there is varying gradients and varying turning points and whatnot. So resetting that, we can increase automatic stabilizer strength. So increasing automatic stabilizer strength to, let's say, 0.5. Now we can compare the changes in GDP trendline. So as you can see, we still have the slight turning point here and there, but that is inevitable no matter how much you increase automatic stabilizer strength, because the economy will never be perfectly correlated, especially with stochastic shocks enable. But we can see overall it's a lot more straight in terms of the trend line. The trend line starts from A to B. The gradients don't vary as much. The gradients do remain the same apart from this little blip here, which is probably due to a higher shock scenario, which is randomly generated. But overall, we do have sort of a stronger positive gradient overall. So we can mark this test as a success as well. The next test is that increasing inflation response strength should lead to the points on the output gap versus inflation graph clustering tight to the 1 to 3% band. So testing this out, resetting the simulation, and we will revert and reset the whole simulation, safekeeping and to results, a rolling graph display length 210. So change it to output gap versus inflation. And we can simulate 30 years with a current inflation response strength of 1.5. We'll decrease that to 1.8 for this test. And simulating 30 years. So you can see around less than half, or around half of the points lie within the 1 to 3% band, and we still have these points up here varying from 3 to 5%, and these points down here varying from 1 to 0%. So resetting the simulation, we should see more points lie within this region once we increase inflation response rate. So increasing to 3.0% and simulating once again 30 years, we should see more points lie within this region here. And as you can see, we have a bit more than 50% of the points are lying within this region here, with the 1 to 3% region. We can compare this to the other one. We can count the points which are not within the region. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points which lie outside the region with a 3% inflation response strength. So now if we revert that back to 1%, so we had 9 points outside of the target bands, and reverting it back to a 1% strength. Let's see how many points lie outside. So we had 9 before, and now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So as you can see, there are more points which lie outside of the target band, meaning that when you increase inflation response strength, you have more points which are clustered within the 1 to 3% zone. We can test this out on a larger scale if we were to go to maybe 50 to 100 points, but that would be a pain to count all those points up. So using our test here, we can mark test 19 as a success as well. Moving on to test 20, is that increase in interest rate smoothing should lead to smaller gradual changes in interest rates over time. So lower smoothing value should lead to larger rate jumps, and a higher smoothing value should lead to smaller gradual changes. You can't test this criteria visually, so we'll be having to use breakpoints within the code and observing the values to see the changes. So we currently have an interest rate smoothing value of 0.7, and if we decrease that to 0.3 for the baseline test, and now we can set an oil and productivity shock for this test. Now, if we simulate the first year, you can see a nominal interest rate of 2.65. Simulating the second year, and you can see a larger jump from 2.65 to 5.45, a much larger jump. And then simulating the third and final year, you can see a decrease in 0.45. And fourth year, 3.57, so near 2% jump decrease. And now resetting this with a higher interest rate smoothing value of 0.8, and following the same principle. So an oil supply shock, first year 2.9, second year 3.6, so 0.7 increase, third year 4.18, fourth year 4.49. So you can see with a higher interest rate smoothing coefficient, interest rate values tend to stay within a 0 to 1% change every year, compared to when we had a 0.3 interest rate smoothing value. We saw jumps of 2%, maybe 2.5% between interest rates. But with a higher interest rate smoothing value, we see smaller incremental values and changes in interest rates. So we can mark that as a pass, because when we increase to 0.8 for interest rate smoothing, the max change we saw in interest rates was 0.7 compared to that of 2.5, which was with the lower smoothing rate. So moving on to the scenario preset shocks, we have three preset shocks: recession shock, oil supply shock, and productivity boom. We'll be carrying out these three tests within the same testing criteria period. So for the first shock test, which is a recession shock, we should see an immediate GDP decrease and a rise in unemployment over that period. Oil supply shock, immediate GDP decrease and inflation rise simultaneously. For a productivity boom, which takes around 10 to 20 years for the boom to kick in, we should see over time an increase in GDP. So testing out now, we can simulate the first 3 years, so we can go 1, 2, 3, apply the recession shock, and when we apply the recession shock, we should see an immediate decrease in GDP trendline, and it should take around 4 to 5 years for GDP to pick back up again and continue its trajectory. So recession shock enabled, simulate, as you can see, immediate decrease, and it keeps getting lower and lower, plateaus around 2029, 2030, and then starts to head back up. Analyzing the GDP, you can see 2025, 2026, 2027 increasing, and then as soon as we hit the recession shock, decreases over this period here, and it starts to pick back up again. Unemployment, same thing, 2027, and as soon as we hit the recession shock, we increase by a lot more, 4.8 to 6.9 to 9 to 10. So throughout this period, we see an increase in unemployment. So we can mark the recession as a pass, and then move on to oil and supply shock. I can once again simulate the first 3 years. The oil and supply shock, due to it being a supply side factor which affects the economy, there is a GDP decrease. It's a smaller than the GDP decrease in recession, because a recession is more, fatal to the economy and the economy's environment. However, we should still see a decrease in GDP. So simulate, and we can see downward trajectory, picks back up again and continues. Analyzing, you can see GDP 2025, 2026, 2027, and once we hit the oil and supply shock, that positive trend line changes and starts to decrease 2028, 2029, and it picks up at 2030, 2031. And then you can witness inflation as well. So from 2027 to 2024, we're in the 1.0, 2.0 range, and then 2028 kicks in, oil and supply shock, 3.48, 3.93, 3.81, 3.80, and then see over this 3-year period, we see increase in inflation, and then it starts to decrease slowly. So we can mark the oil and supply shock as a success. Once again, simulating 3 years. And then if we enable the productivity boom, you won't see results straight away. So we have to simulate around 20 years. So simulating 20 years, we've simulated the first 3 years normally, and then with the productivity boom, let's see the effects in 20 years' time. Upward trajectory in GDP, if we analyze this, 2027, 2028, we see an increase in GDP. As you can see, productivity boom isn't immediate, so there isn't, a significant increase in GDP. But if we witness from 2028, we have a 2.1, and we finish at 3.6. So now we can analyze the effects if we didn't have a productivity boom. So if we analyze the first 3 years, and then we simulate 20 years. View analysis, and yeah, you can see we've ended up with a lower ending value of GDP of 3.356. Hence, we can mark all 3 scenarios a success, as they all did what they intended to do. The next test is test 24, which is a shock intensity multiplier, which is testing the settings tab. So higher shocks should create more volatility in trend lines. We can see that by increased spikes and increased varying gradients. So testing this, resetting the simulation. For safekeeping, we will fully reset the simulation, and then we'll also increase this to 20 so we can visualize the effects more clearer. And then graphs, model sensitivity. So we want to increase, the shock intensity multiplier. So increase in shock intensity multiplier. So first of all, we'll set it to 0.5 times, which is a low multiplier, and then taking it to the GDP over time graph. So we can simulate, let's say, 30 years of this simulation. And you can see that although there are some varying points within the trend line, it's a lot more consistent throughout, especially this period and the ending period. Consistent positive gradient, strong correlation coefficient. And now going back and fully resetting the simulation. Now if we choose a 1.5 times shock intensity multiplier, which is a high value, and we simulate 30 years, we should see a lot more kind of uncertainty and volatility within the trend line, a lot more spikes, dips, turning points, varying gradients, that sort of thing. Simulating 30 years. Yep, and as you can see, consistent the first 2-3 years, goes up, spikes down, and then we do see an increase in consistency throughout here. But for the past 10-ish years, we see a lot of volatility within this region. So not consistent overall, a lot less than that of a low intensity multiplier. So fully resetting the simulation, ready for the next test, and marking this off as pass. The second test we have is automatic stabilizer strength. So we'll be testing between a weak stabilizer strength and a strong stabilizer strength. And with a weaker strength, we should see, once again, same thing with the shock intensity multiplier, more volatility within the GDP trajectory, and with a strong automatic stabilizer, we should see smoother GDP trajectory as shocks are confined and the fiscal policy kicks in automatically when needed. So changing to weak automatic stabilizer strength, and then we'll also do this, follow the same protocol, increase 20 years graph range, and once again we can simulate 20 years. So simulating 20 years with a weak automatic stabilizer strength, varying gradients, more volatility, especially throughout here we can see small pikes here and there. So exiting, resetting fully. And increasing the automatic stabilizer strength to strong, simulating the same 20 years. Now if we increase here, once again we still have the odd spike here and there. We can see a smoother trajectory throughout the trend line. So moving on to test 26, we'll be testing policy responsiveness between low and high policy responsiveness strengths. So higher strengths should increase the effects of changes to policies. We'll be using interest rates as a benchmark example to test the changes in severity between the simulation with different policy responsiveness strengths. So starting off with a low policy responsiveness strength. Simulating 10 years. We'll simulate 20 years, 10% interest rates, and a low policy responsiveness strength. Again, the analysis tab, and witnessing average GDP growth is 2,390 with a low policy responsiveness strength. So 2,390 average GDP growth. And now if we decrease, if we increase policy responsiveness to high, reset simulation, just confirming that's on higher. Once again, simulating the same 20 years with a 10% interest rate, and let's witness the changes in average GDP growth. So you can see average GDP growth is a lot lower than before due to the higher effects of increasing interest rates, and you can see the changes in the policy responsiveness strength and how they impact the severity of policy implementations and changes. So on that basis, we can mark this test as a pass. Moving on to test 27 is a random noise toggle. So when we toggle the random noise checkbox on, we should see jagged trend lines, less consistency, more variation between gradients within the trend lines, and when we toggle it off, we should see smoother, more consistent trend lines. So first of all, we'll test it with it's on, so just to confirm it's on, random noise checked on, simulating 10 years. You can see there is a trend, however, we still have spikes here and there, still a bit of inconsistencies. Resetting the simulation, and then random noise toggled off. Simulate 10 years, and we should see a straight trajectory. So yeah, straight 2000 upwards trajectory, completely straight. So on that basis, we can mark this test as a pass. It tests the boundaries of the graphs. So when the user simulates past a certain point within their chosen graph simulation, they should really reach unrealistic levels within the simulation, and then a message box should appear informing the user that they've reached these unrealistic limits. The message box will persist and continue to be represented to the user after every simulation run. This will only change unless the user re-enters the realistic bounds of the simulation, or if they reach the upper maximum bound. Once they reach the upper maximum bound, it's also indicated they're testing, so GDP, for example, will not increase further. It will clamp to the maximum bound and shall not increase further, and a specific tailored text box should appear, sorry, not text box, message box, should appear to the user informing them they have reached the upper max limit. So testing that now. If we set very generous growth parameters to kind of speed up the process. And simulating 10 years at a time. So you can see GDP has exceeded the upper bound the simulator is reaching unrealistic levels. Try tightening policy. So it's giving you advice on how to re-enter the realistic levels. However, if I continue to simulate, the message box will continue to pop up. Now going for, let's say, 20 years at a time, we finally reached the maximum of the simulation. So it has reached its max, and from this point on, GDP will clamp to its maximum value and the value will not change. Now if we revert back to lower GDP, so 10% spending, 30% tax rates, base of 1%, NBC 0.1, and also enable recession with a higher interest rate. And so we can mark this as a pass. Test 29, output gap versus inflation and regression accuracy. So after simulating many years, there should be a positive regression line spanning the data range properly. So the trend with output gap versus inflation is that over time there is a positive correlation between the two variables. So when we run, let's say 30, 40 years of output gap versus inflation, run a regression line, it should be a positive regression gradient which spans the width of the graph. So reverting back, we reset that, and for safekeeping we'll fully reset the simulation. Okay, so here we can simulate, for example, we'll do 30 years, and we simulate, and if we press regression, we have a strong positive correlation as predicted, gradient of 1.33, positive gradient. So yeah, that fits the sorts of criteria, so you can mark that as pass. Does it span the data range properly? Yes, it does. You can see that it goes through the data range. It doesn't, stop before these points or stop before these points, etc. You can also verify other things like the intercept. So if we go to where the x variable is 0, we go up and then extrapolate horizontally. You can see that the intercept's around 2.5, 2.4, which matches up with intercept here 2.44. So we can confirm the accuracy of the regression model, and we can mark test 29 as a pass. Moving on, regression report visibility and analysis tab check. So after we've run this regression, when we press simulate, this all should disappear, and we should be able to continue with our simulation. Furthermore, we should be able to view the regression details in the analysis tab, and it should be stored there. So simulating, and as you can see, everything disappears, and we can continue. Going back to the analysis tab, you can see right here, most recent output gap inflation regression model, and it shows the gradient and intercept here. So you can mark this as a pass. Next next thing we'll be testing out is that if the averages are being calculated correctly in the analysis tab, so we're not being misled with sorts of indicators that we are being presented with. So to test it simply, we will simulate just 3 years of GDP, go to the analysis tab, and you can see these years here. So it's calculating an average GDP growth of 2007 to 2.76 using these values here. Now to test this out. So the first value we had was 2000 plus 2052.9 plus 2096.49 plus 2141.65, and dividing that all by the number of points we have, which is 4. And we have an average of 2072.76, confirming that with this 2072.76. So therefore we can confirm that this has accurately been calculated and the average GDP growth has accurately been calculated. So we can confirm that this is a pass. Next up, we will be testing these 3 scenarios simultaneously. These are all to do with loading and saving simulations within the system. So you should be able to save and name a scenario, which will then appear in the list box. You should be able to load this scenario, and all the saved data and graph status remains the same. And then the user should be able to delete this scenario, and the scenario should be deleted from the directory within the file folder. As we will need to use these saved scenarios for later on, I'm going to purposely create scenarios. So we'll do a demand side growth scenario, 5% growth, 0.9 MPC, and a low tax rate, 10%. Simulating 10 years, you see GDP growth. So now if we go to the save, we will call this good test, and we can save that. And now, as you can see, it appears here, and we can load. We have our values here, and we can see that it is saved to a specific directory. Here we have good tests, and it stores all the history of our test. So that works. And now we can test the loading feature. So if we were to reset the whole simulation, go back to the simulation dashboard, and we can see that everything's been reset. All the policies have been reset. So now when we load this, all the policies should revert back to whatever was saved in this scenario, and then all the graphs should be reverted back to the same. So exiting, going back, you can see the graph is restored back to a state, tax rate, all the text boxes are restored, 5%, 0.9, etc. So we can confirm that that works. Now we'll create another test. So if we reset, we'll just simulate 3 years, save this, call delete test, and save. And we can see that delete test is saved in a directory. So if we go to the bin and we go to debug file, you can see delete test has been saved. And when we come to delete it, it's removed from the list. And is it removed from the files? Yes, it is. As you can see, the only test remaining in the saves folder is indeed good tests. So that covers all three of these criteria, and they'll pass successfully, so we can mark them down as a pass. The next one is show grid line toggle. So the user should be able to toggle whether they want grid lines on time series graphs, so GDP over time graph, debt to GDP graph, and current account balance should all have the option for grid lines. So toggling it on, and you can see grid lines are now appeared on the time series graphs. And they also line up with the y-axis as well, which is quite cool. So resetting the simulation fully and marking this criteria as a pass. Test 36 is currency display changes. So the user has the option to change the currency which is being displayed on the axis. Depending to wherever they select, they have three options to select from. So they have USD, which is the standard, GBP, or the euro. So we'll change to the euro for this one. And you can see y-axis changed to euro million and percentage of GDP in euros. So we can mark that as a pass. The next one we've already tested before, but for the sake of this individual test, we'll test it again, and that is the rolling graph display length. So the user should be able to change the number of years shown at any one time on the x-axis of graph. So we can do 15 years. And now we can see that should be 15 points shown from 2025, 2039, 15 points shown. So yeah, resetting the back to normal, and we can mark this as pass. The next is the help and instructions tab. The user should be able to view all instructions and all tabs successfully. So help and instructions, you have the first overview tab, how simulation works tab with a scroll bar to access all the information which can be fitted on the screen, the graph guides, and then finally the tips. So yeah, that will work successfully. So we can mark that as a pass. Next up is analysis interpretation. So the user should be able to display an accurate message box explaining potential causes for changes in economic indicators. So reverting back, to save time, we will load this good test. As you can see, there's been an increase in GDP. GDP has increased over time. Debt has also increased over time. Unemployment has increased as well, and so has inflation. So all four key variables have increased over time. So now if we go to the analysis tab, we should be able to look at why our values have increased, our economic indicators have increased over time. So as you can see, GDP has increased over time, tells you why. Unemployment rate has fallen, as seen here. Inflation rate has risen, as seen here, and debt has increased. So it displays preset paragraphs depending on whether the user's economic indicators have increased or decreased over time, and yeah, the user can read through that and see. And to further aid their analysis support, the user also have the option to export their data to a CSV file. So if I press export, you can see that it's been exported successfully. And now if we go to the debug folder, we can see economic history export. And if we click on this, our text file data has been transformed and exported to Microsoft Excel spreadsheet. So that works successfully as well. So we can mark analysis interpretation as a pass. Moving on to test 40 is the rank button. So based off the saved scenarios that the user has, a merge sort algorithm will compare each scenario based off performance targets. So they're weighted based off GDP growth. However, they also take into account the unemployment, current account balance, inflation, debt, etc. And they start off with a score, and the score is deducted as the negative factors come into play for the simulation. So at the moment we only have one safe scenario good test, so let's make a bad test to compare with. So a bad test would be low spending, so 10% spending, tax rate 40%, low MPC, low base growth, high interest. Simulating the same amount of years, which was 10 years, see lower GDP growth compared to the good test. Saving this, let's call that the bad test. So now when I rank these, good test should rank above bad test within the grid. As you can see, you have good test, bad test, higher average GDP growth, highest, lowest score, which indicates higher positioning. And of course, I could save 10, 15 multiple tests and then rank it, and it would rank in order, but for the sake of this video, we're on testing 2. So for that reason, pass. The last 2 tests we can sort of execute at the same time. We've tested out full simulation reset quite a lot in this video, but again, for the sake of the test, we will test out once again. Test 41 is reset policies button. So this just resets the policies. It doesn't reset the graph or any visual effects or anything like that. It just resets the policies within the simulation. So loading the good test up. Start simulation. We can see tax rate of 10%, spending of 22, core parameter 0.95. So when we click reset policies, the trend line should remain the same, and all the policies should be reset to the starting default value. So 20% tax rate, correct. 2% base growth and 0.6% PC. So that is being executed correctly. And when we perform a full reset, so I'll just reload the scenario again. So again, all the text boxes are full of what we left them on. 5% base growth, 0.9 MPC. And if we fully reset the simulation, everything should clear up. The graph should be clear, the simulation text boxes should be reverted to normal, graphs cleared. Text boxes, 2%, 0.6, 20%. So yeah, that confirms that functionality. So that is all 42 tests complete, all 42 tests passed successfully, and that is the end of my testing video for my AQA A-Level Computer Science NEA, presenting Macroeconomic Simulation System by Daniel Hashmi, candidate number A244. Thank you.